All right, today we're going to talk about a different differentiable rule. It's called the product rule. And so it applies if you're taking the derivative with respect to x of two functions being multiplied together. So what it says is you take the derivative of the first function times the second function, and then add on the first function times the derivative of the second function. So we do have to have this product rule memorized. We use it a lot in this class. And so let's do an example. So on number 1, we have h of x, which can be seen as the product of two functions. We'll say like f and g to match that product rule. Okay, so if I'm finding the derivative of h of x, h prime of x, right? So we'll use the product rule, and then we'll talk about how we could also find the derivative a different way. So, okay, so take the derivative of f, what I'm calling f. So the derivative of 3x is 3, and then derivative of minus 2x squared is minus 4x using the power rule. Okay, make sure that's in parentheses. And then the times this g of x, so we don't mess with that, plus f of x, right, times the derivative of g, which is what we're calling g. So 5 plus 4x. So derivative of 5 is 0, and the derivative of 4x is 4. So we can just put 4. All right, and then we want to clean it up, so we'll multiply it out. Okay. And distribute that 4. Okay, combine like terms. Okay, what do we got? 24x minus 20x, and then plus 15. Okay, so that's the derivative, right? So we could at the beginning also just multiply out the function, right? So I'll just show an alternative way. So let's just rewrite h of x in standard form. So what would that be? 15x plus 12x squared minus 10x squared minus 8x cubed. Okay, clean it up a little bit. Okay, and then if we take the derivative of this in standard form, right, we get negative 24x squared using the power rule plus 4x plus 15. Right, so you can see it's the same thing. All right, so let's do part B. So B, we got these two functions being multiplied together to make up f of x. So we're going to apply the power rule. All right, so the derivative of the first function in parentheses will be 3x squared plus 2, right, times the second. All right, and then plus the first function times the derivative of the second. Okay, and then just like before, we just multiply it all out. All right, so I skipped ahead to multiplying it all out, and so this is the derivative. All right, okay, let's move on to part C. So part C, we got g of s equals this. And so we talked about when we learned the power rule that we need to be able to rewrite a function sometimes, so we can use the power rule later. So let's rewrite it to be s to the 1/2 times 4 minus x squared. Okay? And, okay, let's use the product rule. Okay, so this times this is what we're looking at. Okay, so the derivative would equal, okay, so the derivative of s to the 1/2 would be 1/2 s to the negative 1/2 using the power rule times 4 minus s squared plus s to the 1/2, and then times the derivative of 4 minus s squared. So The derivative of 4 is 0, and so the derivative of minus s squared would be minus 2s. Okay? And let's see. All right, so let's distribute here. So what is that? 2s to the negative 1/2, right? And then here, minus 1/2. So we're multiplying common base, so we add the exponents with the s's. So 2 plus negative 1/2 is 3/2. And then over here, that's minus 2s, right? Same thing, multiply common base, you add the exponents. So 1 plus 1/2 is 3s. All right, we can combine those. What is that? Minus 5/2 s to the 3/2. Right? Or we could rewrite it in radical form. Okay, and so a different way you could do it is like at the very beginning. So we'll just go ahead and establish this. This is our derivative. So here, a different way to do that one. Let's see if I can work it off to the side over here. Right, is when we had the function written as this, right, we could just distribute right off the bat and then apply the power rule. So let's see if that works out as well. So s to the 5/2, right? Because you're multiplying common base, you add the exponents, and then you can take the derivative of this. So you get, right, 4 times 1/2 is 2, and then s to the 1/2 minus 1 is negative 1/2, and then minus 5/2 s to the 3/2, right? So you see it's the same thing as that. So either method is fine. You could do the product rule like what we did over here, or multiply it all out and use the power rule once you have it in standard form. Okay, okay, let's jump to this part here. Okay, part D. This is a typo. Okay, so we're gonna apply the product rule here because we can see it as 3x squared times sine x. Okay, so the derivative would equal, okay, the derivative of 3x squared is 6x times sine x plus 3x squared times the derivative of sine x is cosine x. And that's it. We can't do anything with that, so that is our derivative. All right, here we're going to talk about higher order derivatives. So if you wanted to find the second derivative, its notation is commonly f double prime of x. And so the way you find the second derivative is you take the derivative with respect to x of the first derivative, okay? And so some other common notations of the second derivative are d2y over dx squared. So if you're curious where that notation comes from, it's where you're taking the derivative with respect to x of dy dx, right? So this, all that says is you're taking the derivative with respect to y again, with respect to x again. And d2f over dx squared is another common notation for the second derivative. But we'll use that notation later. Okay, so let's find the first 5 derivatives of this function. Okay, so the first derivative, so we just have to apply the power rule and the constant rule at the end. So we get 20x cubed plus 9x squared minus 30x plus 20 plus 0. All right, and then the second derivative would be 60x squared plus 18x minus 30. Okay, the third derivative, we can do triple prime, f triple prime of x equals 120x plus 18. All right, and then if we want to take the fourth derivative, this is the notation. We stop using prime symbols once we get past 3. So we'll use that notation to represent the fourth derivative. So that would just be 120, and then the fifth derivative would be 0. All right. And so some higher order derivatives in applications would be something where we've dealt with position, velocity, and acceleration. So we've talked about before that position is typically represented by the function s of t. And so we know the rate of change of position is velocity. So velocity is equal to the first derivative of position. And we've talked about how acceleration is the derivative of velocity, right? Or the second derivative of the position function. Okay, so when acceleration and velocity have the same sign, so if they're both positive, meaning they're both going in the right direction, or if they're both negative, right, meaning acceleration and velocity are both pointing to the left, we say the object is speeding up. And if acceleration and velocity have different signs, then the object is said to be slowing down. And so, quick visual to kind of explain why that is. So let's say you have you're in a car and you're driving to the right with a positive velocity, but you apply the brakes. So you have a negative acceleration, you'd be slowing down. Okay. But if your velocity is in the right direction and you're stepping on the gas at the same time, so you're accelerating to the right as well, you'd be speeding up. Okay. But if you're driving to the left with a negative velocity, and you're also accelerating in that direction, then you'd be speeding up as well. Okay? But if you are having a velocity in the left direction, right? But you apply the brakes, so you'd be having a positive acceleration in this case, you'd be slowing down. Okay? So all you need to know is if you're speeding up, that means your acceleration and velocity are both the same sign, positive, or negative. And if it's a different sign for both velocity and acceleration, you're slowing down. Okay, so look at number 3. So a car traveling at a rate of 66 feet per second. When the brakes are applied, the position function is given by that, where s is measured in feet and t is measured in seconds. Find the car's position, the car's velocity, and the car's acceleration at 2. Okay. So we can find s of 2 first. Okay, just plugging in 2 into s of t. And what is that? Negative 33 plus 132 is 99 feet. So don't forget the units. Okay, and then the velocity. You're going to find the velocity by taking the derivative of position. So apply the power rule. So what is that? Negative 16.5 t, right? Taking the derivative of that. And then the derivative of 66 t is just plus 66. Okay, so the velocity at 2 seconds plus 66. What is that? Negative 33 plus 66 is 33. And since it's velocity, it's feet per second. Okay, positive velocity. Okay, the acceleration would be the derivative of velocity, right? Or the second derivative of position. So that would just be negative 16.5 t. And we want to find the acceleration at 2 seconds. Oh, my bad. There's no t there. So it's just negative 16.5 feet per second squared. Okay. So at 2 seconds, it doesn't ask this, but it's good to see it. Since we have a positive velocity and a negative acceleration, we would be saying the car is slowing down because the signs are opposite in velocity acceleration. So the car is slowing down at t equals 2 seconds. Okay, so these questions on this page are about particle motion. So first question, a particle is moving along a horizontal line and the velocity of the particle is given for various times. Okay, so over the interval 2 to 8, which of the following could be false? So we could reject A and B because they're about the acceleration being 0 and the acceleration being -7 on those intervals, which we don't know what the acceleration is, the rate of change of velocity is. So, but you'll notice that the structure of all these answers are based on the intermediate value theorem. So we can see that our lowest velocity happens at -6, right? And our highest velocity happens at 50, right? So we know our velocities have to be somewhere between at least -6 and 50. So D would be the appropriate answer because we don't know if a velocity of -7 exists in this interval, right? Because -7 is below -6. All right. The next question, the velocity of a bug moving along the y-axis is given by that equation, x squared times f of x. So is the bug speeding up or slowing down at x equals 2? Okay, so we know the velocity, right? So our acceleration, right? Our acceleration, we would need to use the product rule to take the derivative, since we have two functions we multiply together. So, okay, so the derivative of x squared is 2x times f of x plus x squared times the derivative of f of x. Okay, so we want to find, the velocity at 2 and the acceleration at 2 to see if it's speeding up or slowing down. Okay, so the velocity at 2 would be 2 squared times f of 2, right? And so f of 2 we see is -1. So that would be 4 times -1, which is -4. Okay, so we have negative velocity. All right, so back to our acceleration. So our acceleration at 2, right, would be 2 times f of 2 plus 2 squared times the derivative at 2. Okay, so this is 4 times -1 plus 4 times the derivative at 2 is -4. So this ends up being -4 plus -16 is -20. Okay, and so since the velocity and the acceleration have the same sign, they're both negative, this means that the bug is speeding up at x equals 2. Okay, this question, Steve is driving a car during the interval 0 to 6, and the graph of his velocity is shown below. Okay, so this is the velocity. Okay, at which of the labeled points is the car speeding up? So we would say where the velocity and the velocity and acceleration have the same sign, that's where it's speeding up. So at point A, that is where the velocity, we can see, is above the x-axis, so it's positive velocity, and it's got a positive slope, so the acceleration is positive as well. And the only other point where the velocity and acceleration are the same is at D, right? Because you can see we have a negative velocity, because under the x-axis, and then the slope is negative, so that means the acceleration is negative. So A and D, since the velocity and acceleration are the same sign at these points. Okay. Okay, the next question says, okay, on what intervals is Steve speeding up and slowing down? Okay, so let's analyze this. So at the beginning, from 0 to 2, we have a positive velocity because it's above the x-axis. And then the acceleration is positive because we have a positive slope. It's increasing, so positive acceleration. So it's speeding up on this interval 0 to 2. Okay? And then it's also speeding up from 3 to 5 because the velocity is negative and the line is decreasing, so it has a negative slope. So it's got negative velocity, negative acceleration. So it's speeding up there as well from 3 to 5. Okay? And then from 2 to 3, we have a positive velocity because it's above the x-axis, but it's a decreasing line, so it's a negative acceleration. So from 2 to 3, we're slowing down. And then 5 to 6, we're slowing down as well because we have a negative velocity, but the slope is increasing, so we have positive acceleration. So different signs of velocity and acceleration from 5 to 6, so it's slowing down there. Okay, we're going to revisit using the product rule and finding slopes of tangent lines. So number 7, given this function, find the slope of the tangent line at pi over 2. Okay, so that implies that's at x equals pi over 2. Okay, so we want to find the derivative in order to find the slope of the tangent line. Okay, so this first term here, we have to apply the product rule. All right, so the derivative of x cubed is 3x squared times cosine x plus x cubed times the derivative of cosine is negative sine x. And then minus 2 sine x we want to take the derivative of. So minus 2 cosine x is the derivative of that. Okay, so to find the slope of the tangent line, we need to plug in pi over 2. Okay, so we'll simplify this. 3 pi squared over 4 times 0, right? Cosine of pi over 2 is 0, plus pi cubed over 8 times negative 1, because the sine of pi over 2 is 1. And then minus 2 times 0. Okay, so let's see, what does that leave us with? Those terms zero out, so it ends up just equaling negative pi cubed over 8 is the slope of that tangent line. Okay, so on number 9, we are trying to find the limit as h approaches 0 for that expression. And one thing we have to recognize is this is the definition of the derivative format. So, right, so the derivative equals the limit as h approaches 0 for f of x plus h minus f of x all over h, okay? And so if the function that we're trying to find the derivative of is cosine x, what's the derivative of cosine x? Negative sine x. That's the answer. Okay, so here's just a little bit of review about differentiability. So remember, a function is not differentiable at points where it has a discontinuity, like a jump, hole, vertical asymptote, a sharp corner, or a cusp. So a cusp is something like that. Or a vertical tangent line, like right here, right? Because what would be the slope of a vertical line? undefined. So the derivative wouldn't exist at such a point. Okay, so we want to, part A, find the values of x in this interval -4 to 4 at which g is not continuous. Okay, so we see there's a jump at -2, and at +2 there's a removable discontinuity. So those are the places where it's not continuous on that open interval. Okay. B says, okay, find the values of x on that interval at which g is not differentiable. So wherever something's not continuous, it'll also not be differentiable there. So at x equals -2, 2, and also notice there's this cusp at 0. So the derivative wouldn't exist at 0. So it's not differentiable there.